So, the last thing that we talked about is I gave you all. I gave you all an example of, some examples. And then gave you in particular one that was, most of the kind of standard examples of Prufer domains that aren't Ethereans, but are interesting or Bezier. So I gave you an example of a Prufer domain where not all finitely generated ideals were in fact principal. And the last thing I gave you, I believe, was some equivalent conditions on Prufer domains, most of which we've already seen them. So let me give you the following theorem. Let R be a Prufer domain in quotient field K. And let B be a evaluation overring. Of R. Then B is equal to R localized P for some P. Now, what we do know about Prufer domains is part of this is not surprising, right? What we do know about Prufer domains is if you start with a prime ideal P and R and you localize there, then you get a valuation domain. I mean, that's the definition of Prufer domain. What this says a little something extra, because what this says is, in fact, if you have any valuation over ring, it turns out to be a localization. The proof. So let me kind of emphasize this. Any valuation over ring is a localization. So there aren't any sort of hidden valuation domain, valuation over rings that you can't obtain in this fashion. Proof. So take your favorite valuation over ring, B. Well, what do you know? I mean, it's got a maximal ideal. Take that maximal ideal M and contract it down to R. Now, as I probably suspect, we want to show that V is in fact R localized at R localized at P. No. If S is in R, but not in P, then S is a unit in V. Right? Because S, of course, being an R, is of course also in V because it's an overring. And if it misses P, that means it misses that maximal ideal, so it has to be a unit. So in particular, S inverse is in V. Therefore, if R over S is in plus P, then R over S, which is R S inverse, can be. So this localization is actually contained in V. For the other containment, for the other containment, we want to show, of course, that V is, everything in V is actually in that localization. Note that our localized P is evaluation domain, because R is Prufer. That's where we use, of course, the assumption that R is Prufer. Now, suppose that V is in V, of course, I want to show that V is in this localization. If V is in V, I'm sorry, RP, then done. And if not, then what do we know? If V doesn't live in R localized P, then that's right. Then because of the fact that R localized is valuation domain, then and in fact, you can go further than that. In fact, you can say, in fact, you can further say that not only is V inverse in R localized P, in fact, it has to be the maximum ideal of that. Because otherwise, if it's a unit, then V is in there in the first place. So V inverse is RS and R localized P. That is to say, S is not in V. All right. And so excuse me, hence, S is RV, which must be in the maximal ideal of V. Right? Just clearing this out, this of course means S is RV, but of course R, since this thing is actually a non-unit, R must be in the maximal ideal of V. Therefore, S is in M. And that establishes the theorem. So any valuation over any Prufer domain is in fact localization. Let me give you an example to maybe illustrate how things could go wrong. Consider you create a value on quotient field is this. And let me kind of give you, basically what you do is you kind of squeeze X and Y together, right? That's essentially what happens here. So in this valuation overring, look at the elements X and Y, they both divide each other. So I'm going to use that valuation. So in other words, what that means is X associates that. But this valuation rate cannot possibly be a localization. Overring cannot be local. Yeah. And, but no surprise here because fxy is not a Prufer domain, right? There's many localizations here that are not valuation. In fact, if you localize this ring at the maximal ideal xy, the maximal ideal in the localization is finitely generated, but not principal. Right.
So why can't this be a localization?
Well, I wanted to kind of leave that to you to kind of figure out, because I think it would be good to think about this. But imagine what you have. You have to take, so let me get you started. In this localization here, at a prime ideal, associates and both X and Y non-units. I mean, you could certainly take the quotient field and those two would be associate, but I also, in this valuation I'm bringing, I also want to keep X and Y to be non-units. So think about why you can't do that. Because remember, in the localization, what you have is everything should be a fraction of polynomial in two variables over something that's not in this prime ideal, and see if you can run into problems with that. Okay. I'm going to tie this up here. Let me give you the following theorem. Actually, I'm just going to quote this for notes. You all already did this for me. Any overriding proof domain is again a proof domain. So this is one of our earlier homework exercises. Okay. let me give you a longer list of equivalences for Prufer. Some of these you already know, but I'm gonna use this theorem to kind of, tie things together. There, 507. Like I said, some of this will be an old chestnut. This will tie things together nicely. What are the integral domain? The following conditions are equivalent. And a domain satisfying one, hence all of them is called a Prufer domain. Number one, every finitely generated ideal is invertible. Last two, RP is evaluation domain. For all P in spec R. Number three, RM is evaluation domain. For all M in max spec R. Number four, every overring of R is integer closed. Every overring of R is an intersection of localizations of R. Every overing of R is an intersection of localizations. Um, and six so the last one is almost. So another way to put this is every overing of R has any of these five equivalent properties. So let me say something about this. We've seen the connection between the first four. In fact, I gave this last time. So there's kind of two other equivalences here. Can somebody talk me through why we can latch five on to the rest of them now?
You have against Prufer. And therefore, it's next, intersection of, its localizations. Those localizations are valuation over ranks of R. So we can use that theorem that we just proved.
Right. So if you have an overring of R, what do I know about it? From this condition, I know it's integral closed. Right, so your overring is now an intersection of valuation overrings. And the valuation overrings are localizations, and so there you go, right? It's certainly true, we've already shown, you've already shown that an overring proof domain is Prufer. And of course, if every overring, then that includes R itself. So there are many more. I think at some point, so this is dated, there's probably more like, there's something like, if you recall, Dedekind domains, I brought that up when we first talked about Prufer. What's the relationship between Dedekind and Prufer?
Can this Prufer with dimension one?
Oh, you're close, that's a necessary, but it's not quite enough. Yeah, it has been the theorem, right? It is possible to have one-dimensional Prufer domains that aren't Noetherian. Unfortunately, but, yes, if, I think for Dedekind domains, which are the Noetherian Prufer domains, there's something like 50 equivalent conditions in the literature. In fact, an old friend of mine actually proved one of them in his PhD thesis. It was something like, LCM stable in the power series extension gives you Dedekind as well. So there's a zillion of these things. There's even more, I think, for Prufer. And Prufer they're kind of magical because one of the things about algebra that everybody likes is polynomial equations. And Prufer and Dedekind domains are very intimately related to polynomial equations and also factorization, right? They're closed, they have these nice localizations, and Prufer domains show up in number theory a lot. For example, most number theory that you look at algebraic number theory, you look at a finite extension of the rational numbers and the integral closure of Z, and that's a ring of algebraic integers. These things are always Dedekind. Prufer domain, so they're Prufer. Prufer takes it further because it turns out that if you have an infinite extension, if it's algebraic, then it may not be Dedekind anymore, it may not be Noetherian, but it's always going to be Prufer. So here is the next theorem. Here we're going to let K be a field and X just an indeterminate. If V is evaluation, well, let's let V be evaluation domain between K and KX. So V is just some valuation domain that lies between K, the field K, and rational functions and the variable X over K. And I want it to not be the whole thing. Actually. Right, this is the theorem, but I don't want it to be either one of them. I want it to be evaluation domain that sits properly between these two fields. Oh. And KX is Okay, so let me give you a word of caution here. So I didn't really have to put that K in there because the next condition I want is I want, I want K of X, I'm sorry, I want V to be so big that K of X is its quotient. Right, so that means that it couldn't be this then, could it? Right, so we don't really need this, although I'm correct to write that. Let me give you a word of caution. Notice that notice that K of X squared is a field that lies between K and KX properly. Everybody agree with that? And so it's a field, so this is valuation domain, but it can't be this because notice that the quotient field of this is still bigger than the quotient field, right? So in other words, what I'm trying to communicate to you is V has to have enough junk in it so that the quotient field is actually all of KX. So you have to get X in the quotient field somehow. Then V, the neat part of the theorem is I can tell you exactly what V is. V is either the polynomial ring Kx, which is a PID, localized at one of its primes, or V is, so if you have the valuation domain and it's robust enough to where the quotient field, is, of this valuation domain is actually all of the rational functions, then V is either, Kx localized to some prime. Right, and notice this is a PID, notice that of course the quotient field of this is Kx. Or it's K adjoined with X inverse, localized at X inverse. It's one of those two. Okay, so let's prove this. This is kind of an interesting little theorem. At the outset, so let's kind of get this straightened out from the very beginning. Either X or X inverse is in V. Right, because V of course is a valuation domain and its quotient field has to be all K of X. So X is certainly in the quotient field of V by assumption, so either X or its inverse has to be an element of V. If, case one sort of, if X is in V, then KX is in V, right? Because all these rings contain K. So if you've got X is in V and all of K is in V, then maybe you gotta have at least KX living in V, right? So you gotta have that. And so V is a valuation over ring of KX, right? So V is a valuation over KX.
Yes, okay, that must prove it.
Exactly. Good. KX is a PID. So in particular, it's Prufer. And and because of its PID, so if it's Prufer, what do we know? We know that, every overring is an intersection of localizations, right? But for a PID, we know something even better, right? So V is a localization. Uh, KX. And since it's a valuation domain, V is KX localized P. Sometimes P.
What do you need V as localization? And since V is a valuation domain, what extra is there?
Well, this is also a proof of domain, right? And so we know that, if this is a valuation domain, it has to be a localization at a prime. Right? Because I know the PID, any overring of a PID is a localization in general, right? It's localized to some set. But in fact, the overring in our case is in fact a valuation domain. So that means that set has to be the complement of a prime ideal.
Okay.
Right?
So I guess what I'm asking is, why do we have this first statement, and so V is a localization of K bracket X? We didn't really, because what we're really using instead, the theorem we just proved that every valuation overring or Prufer domain is a localization out of prime.
Yeah, you can probably trim it a little bit. Yeah. Yeah, I just pointed out this exercise we know earlier.
Thank you, sorry, I was just confused. the first one.
So that gives kind of first, so there's this suspect that came out of our search, right? And notice that, let me take us back to it. I know that P is non-zero. Yes, you could localize at zero. What happens if you localize at zero? You get the entire KX, which is a no-no, right? So this prime ideal must be non-zero. And we know in a PID that's generated by an irreducible polynomial, right? Everybody cool with that? Okay, well, that's what happens if X is in V. If X is not in V. So we've got this covered if X is in V. So if X is not in V, then KX inverse is strictly contained in V. I know it's strictly contained in V because V is valuation domain and KX is never, KX is, well, this is KX inverse, but this is isomorphic to KX, right? So this is a polynomial ring in the variable X inverse, and that's got infinitely many maximal ideals. This is not a valuation domain. And so again, V X inverse localized at some prime ideal P. And since X is not in V, then X inverse is in maximal ideal And so, in fact, the prime ideal must be generated by X inverse. The strict containment means that X is not a unit in this, whatever this valuation domain is. So it must, so X inverse must be in this prime ideal that you've localized at. And so that's the only one it can be, right? Okay. Any questions on that?
Sorry, why did you say strictly? Why is this strictly contained in V?
Well, again, because K is contained in whatever, and if X is not in V, then X inverse is in V. So now you've got KX inverse in there. And this containment, just like in the previous one, but I emphasize it here, KX inverse must be strictly contained. It's contained in the valuation domain, but it can't be the valuation domain itself because it's got infinitely many maximal ideals. All right. Let me, I'm not gonna prove the next theorem because I already have, because this is the one where I kind of goofed up and gave you all the problem that depended on this too early. So we've been through the proof of this, but I think it will be useful for me to give it back to you right now. Now, let R be quasi-local and intervally closed. Quasi-local. Intervally closed. Domain. Your quotient is okay. If you have an element, U and K, is a root of a polynomial let's call it R0, R1X plus RNXN and RX with at least one RI, a unit in R, then U or U inverse is in R. So this is a really neat generalization of the notion of Monte polynomial. Of course, it is in a pretty specific situation, right? For this to fly, R has to be quasi-local and interval closed. But if it is, and you've got an element quotient field that is the root of some polynomial, and at least one of those coefficients is a unit, then either the element itself or its inverse has to live in R. We can prove this already. And this allows us to do the following really groovy theorem that I kind of hinted at a little bit earlier. Theorem. Five, 0, 10. Let R be a Prufer domain with quotient field K. And let's suppose that we have an algebraic extension, we'll call it f of k. And f an algebraic extension of k. So f is a field extension, like in the old days we got Y theorem, we talked about algebraic extensions. If T is the integral closure of, what was it, R in F, then T is also a proof domain. Draw like that, this is really kind of cool, right? So, for example, so here, I like to draw a diagram of this theorem a little bit to kind of get a picture of what's going on. So, if you have the following situation, so this animal right here is Prufer. And this is the quotient field. Now you extend this field. This is an algebraic extension. But the cool thing is it can be as big as you want, right? And you don't have to do this wimpy kind of crap that we did before. Oh, we got a finite extension. You can go crazy as long as it's algebraic. Then take T, the interval closure of, let's see if I remember the notation. Interval closure of R in F. T. So this is of course the set of all stuff X in, well, we call alpha and F, such that alpha is root of monic polynomial in Rx. So if you take this animal right here, this one is also proof. Let me show you a situation where you see this come up a lot as far as applications. So in particular, you might have and then you have where this extension is algebraic. Let me point out that Z is in fact a Prufer domain, right? It's in fact, it's Dedekind, right? Because it's Prufer and it's a theorem. And the situation that you encounter in Galois theory and algebraic number theory often is this extension is finite is the lazy person's algebraic, right? Because any finite extension is algebraic, but the converse isn't true. So in the situation in number theory, this is a finite extension, hence it's algebraic. Now take T, the interval closure of Z and F, and this one will also, this extension, so according to this theorem, will be Prufer. And we're going to see later that in this particular, if it's finite, it's also in the theorem. And so T would also be a Dedekind domain. That is the machine that makes a lot of algebraic number theory work. You get these nice Dedekind domains here. However, this theorem says we don't have to assume finite. We can take that off the table as long as algebraic. So in particular, I can let this field be the algebraic closure of Q, right? And this is a big ring, right? When you take the integral closure of Z in that. However, it's still Prufer, right? It's amazingly a message Prufer. There's all kinds of crazy stuff that happens here. It turns out that if this is the if this is the algebraic closure of Q, then this ring right here, well, take your favorite prime here, say two. If you look at two up here, it is contained in infinitely many maximal ideals. However, all non-zero prime ideals are maximal. So this one's still one-dimensional, but every prime is contained in infinitely many maximal ideals, and the valuation domains are non-discrete. It's a mess, but it's still Prufer, right? And so you get some nice consequences of that. Okay. Any questions on that? This theorem is so fun that I think we're gonna cut out today, and I'm gonna prove this next time, because I wanna break up the excitement here. But let me encourage you all to be at the math club, because Daniel Martin's talking to everybody. It should probably be a good one. Okay, any questions before we go? What, did I do something fun?
Well, I guess my question is, do you ever say that somebody's not potentially gonna be a really good one today for math club?
Well, for all you know, I just reject a whole bunch of people for talking in math. No, actually, it's not surprising that I say this, because these are people that volunteer to do it. And so usually they're pretty excited or whatever.
Right.
If I actually had to go out and recruit somebody and grab them by the collar and say, you know, that would probably be where maybe you should go home and watch Gilligan's Island. So before to answer your question, probably no, but I'm